seamount deep beneath the ocean surface has generated discolored water plumes and may result in the release of floating pumice stones that could drift across the ocean surface. In response to this eruption, the Northern Mariana Islands Volcano Observatory raised the volcano alert level to advisory and the aviation color code to yellow, signaling a potential threat to surrounding regions and increased volcanic activity. This event is part of an ongoing eruption sequence of the seamount which has been under closer scrutiny since August 2024, drawing scientific attention due to the possibility that it could trigger larger, more dramatic volcanic events. Far from being an isolated incident, this eruption serves as a powerful reminder of the massive forces continuously reshaping the Earth's crust beneath the ocean surface. The seamount, located approximately 18 kilometers southeast of Ferrolán de Pagaros in the Northern Mariana Islands, lies about 75 m or 246 feet below sea level and is part of the larger Mariana Volcanic Arc, a chain of underwater and above-ground volcanoes spread across the western Pacific Ocean. This geologically active area is driven by the intense tectonic forces at the subduction zone where the Pacific Plate plunges beneath the Philippine Sea Plate. It is this tectonic collision that creates the ideal environment for volcanic activity, building and feeding formations like the High Seamount. This volcano has a history of recurring eruptions, with a previous eruptive phase documented between October 2022 and May 2023. The repeated activity has captured the attention of volcanologists who now employ advanced satellite imaging and hydrophone arrays to study it. Given the remoteness and inaccessibility of the seamount, remote sensing technologies have become vital for monitoring such underwater volcanoes. These systems provide critical data in the absence of land-based seismic stations, which are often non-existent near submerged volcanoes. While land-based volcanoes are monitored using comprehensive seismic networks, underwater volcanoes like this one require a different suite of tools, such as satellite imagery to detect changes in water coloration and surface temperature, and hydroacoustic sensors that capture the sound waves generated by eruptions. Interestingly, the current eruption did not trigger any strong hydroacoustic or seismic signals, meaning scientists had to rely almost entirely on visual and satellite-based data to confirm and track the event. This underscores the complexity of monitoring underwater volcanic activity, particularly in remote regions with limited infrastructure. The seamount's location within the Mariana Arc further complicates matters. Given the region's dynamic geological nature, the Mariana Trench, Earth's deepest oceanic trench, is not just a dramatic topographical feature, it plays a crucial role in the tectonic and volcanic processes at work. As the Pacific Plate descends into the mantle beneath the Philippine Sea Plate, it releases trapped volatiles such as water and carbon dioxide. These volatiles lower the melting point of the overlying mantle wedge, producing magma that slowly rises and eventually fuels eruptions like the one recently observed. This long-term geological process has built the Mariana Arc over millions of years and continues to shape it with each new eruptive phase. The seamount has evolved significantly through past eruptions. One example is the explosive 2014 eruption, which was detected using both hydroacoustic sensors and distant seismic stations. That event created a new summit crater and initiated a major landslide on the southeastern flank of the volcano, clearly demonstrating the potential for substantial structural changes on the seafloor due to volcanic activity. In many cases, these underwater eruptions build new geological features, such as ridges, craters, and volcanic cones over time. More recently, between December 2023 and April 2024, another eruptive phase was recorded, confirming the seamount's continued status as an active submarine volcano. Even earlier, in 1979, a fishing crew near the summit reported experiencing strong vibrations and shocks. Early anecdotal evidence of volcanic unrest and subsequent scientific observations confirmed the upwelling of sulfur-rich water, signaling volcanic disturbances below. Although the High Seamount is situated in a remote area of the Pacific Ocean and poses little immediate threat to human populations, it remains a potential hazard to maritime navigation. Mariners operating in the region have been warned to exercise caution. Floating volcanic pumice capable of damaging ship hulls or interfering with engines is one of several risks posed by submarine volcanic activity. In addition, the sudden formation of new underwater features or shallow ridges could alter local bathymetry and pose hazards to vessels. These practical threats reinforce the need for ongoing observation despite the logistical challenges involved. Even when not directly affecting human settlements, underwater eruptions have broader implications for global scientific research and marine ecosystems. Understanding how and why the seamount formed provides insight into its ongoing activity. Like many volcanoes in the Mariana Arc, the seamount was born from subduction-related volcanic processes. As the Pacific Plate subducts westward beneath the Philippine Sea Plate, it melts and produces magma that eventually surfaces through fractures and weaknesses in the oceanic crust. Over millions of years, successive volcanic eruptions have added layers of hardened lava, ash, and other materials to the structure, building it into the high seamount we see today. Though its summit lies just 137 meters below the ocean surface, it has yet to emerge above sea level to form an island. However, its persistent volcanic activity suggests that future eruptions could eventually breach the ocean surface, creating a new land mass. In this way, the high seamount serves as a living example of how underwater volcanoes contribute to Earth's continual geological transformation. Adding to this geological complexity is the Back-Arc Basin located behind the Mariana Trench, where seafloor spreading further reshapes the ocean floor. This combination of subduction at the trench and spreading behind it creates a unique and constantly changing geological environment. Though the high seamount is part of the broader Ring of Fire, a vast horseshoe-shaped zone of intense tectonic activity encircling the Pacific Ocean, its eruptions are driven primarily by local geological conditions. Volcanic systems within the Ring of Fire are mostly independent, influenced by their own tectonic and magmatic settings. Consequently, an eruption at the high seamount is unlikely to directly trigger volcanic activity at other locations. However, some scientific studies suggest that large-scale tectonic or volcanic events, such as earthquakes or massive eruptions, can alter regional stress fields within the Earth's crust. These changes may indirectly affect nearby volcanic systems by adjusting magma pressure or pathways, potentially triggering eruptions if those systems are already under significant internal pressure. This phenomenon, known as dynamic triggering, is relatively rare and generally limited to closely spaced volcanic systems. When comparing the high seamount's current eruption to other notable underwater volcanic events, such as the 2022 eruption of Hunga Tonga Hunga Ha'apai, key differences emerge. The Hunga Tonga eruption was one of the most powerful volcanic explosions in recent history, causing widespread atmospheric disturbances, shock waves that traveled around the globe, and even measurable impacts on sea level and weather patterns. In contrast, the high seamount's eruptions have remained more localized in their effects, though they are geologically significant and potentially hazardous to regional navigation and marine ecosystems. Each volcanic system has distinct characteristics: magma composition, eruption style, tectonic context, and while they may share broad similarities due to their placement within the Pacific Ring of Fire, their individual behavior varies greatly. Ultimately, these eruptions not only transform the seafloor but also enhance our understanding of how Earth's geological systems function, especially in active subduction zones. Underwater volcanoes like the high seamount are key to unraveling the complexities of Earth's interior, particularly the ways in which tectonic plates interact to produce magma and reshape the crust. Modern technology, such as satellite remote sensing and hydroacoustic monitoring, allows scientists to gather crucial data about these hidden but powerful systems. While the seamount's eruptions may not generate headlines like terrestrial volcanoes do, their scientific value is enormous. These underwater events offer an unparalleled window into the forces shaping our planet, forces that operate continuously, often unseen, yet with the potential to dramatically alter the landscape above and below the ocean surface. As scientific research advances, so too does our capacity to understand, anticipate, and adapt to the dynamic processes that govern our world, from the seafloor to the sky. Despite its frequent activity, the high seamount remains a relatively obscure geological feature due to its remote location in the vast Pacific Ocean. This isolation has spared human populations from direct harm, but has not eliminated the risks associated with its eruptions. Volcanic activity beneath the sea poses threats primarily to maritime navigation. Floating pumice, discolored water, and underwater debris can endanger passing vessels, especially those unaware of volcanic hazards in the area. Mariners are routinely advised to maintain heightened awareness when traveling near active seamounts, as sudden eruptions could send debris to the ocean surface with little to no warning. Monitoring such hazards has become increasingly dependent on technology. Traditional seismic networks, which effectively track terrestrial volcanoes, are of limited use under the ocean. In the case of the high sea mount, the absence of nearby seismic stations requires researchers to depend heavily on satellite data and hydroacoustic equipment. Satellites can detect changes in ocean color caused by volcanic plumes or track subtle sea surface temperature anomalies. Hydrophones, meanwhile, are capable of capturing sound waves produced by volcanic eruptions, submarine landslides, or even gas release. However, during the current eruption, these instruments have not picked up significant acoustic signals, leaving scientists to rely mainly on visual cues from orbiting satellites. This underscores the technical and logistical hurdles of studying volcanoes that lie beneath kilometers of water. The geology of the region further adds complexity to the situation. The Mariana Trench, located near the seamount, is the deepest natural point on Earth, reaching depths of nearly 11,000 m. It plays a fundamental role in regional tectonics, as the Pacific plate subducts beneath the Philippine Sea plate along this trench. This subduction generates enormous pressure and heat, creating the ideal conditions for magma formation. Over millennia, this process has given rise to the entire Mariana volcanic arc, a chain of submarine and island volcanoes stretching across the western Pacific. The high seamount, situated southeast of Ferroland de Pagaros, is a product of this tectonic activity. Its summit lies just 137 m beneath the ocean